Acid-base theories. So the first theory, or definition we'll talk about, is the Arrhenius definition. An Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions, H+, in aqueous solution. So for an Arrhenius acid, the key thing here is if you have this H+ proton present, that will tell you have an Arrhenius acid. And Arrhenius acids are molecular compounds with ionizable hydrogen atoms. Their water solutions are known as aqueous acids, and all aqueous acids are electrolytes. So we see a diagram here. We have nitric acid plus water. It's going to produce the hydronium ion and the nitrate ion. And we'll talk about how these protons transfer with our second theory or definition. So some common aqueous acids we see here, and then they talk about strong acids and weak acids. We see those here. So we have HI, HClO4, HBr, HCl, H2SO4, and HClO3. We also can have for a strong acid, we could have HNO3. And then we see our lists of weak acids as well. So, strength of acids. So a strong acid is one that ionizes completely in aqueous solution. So a strong acid is a strong electrolyte. And we went through some of these last slide, HClO4, HCl, HNO3. A weak acid releases few hydrogen ions in aqueous solution. Hydronium ions, anions, and dissolved acid molecules in aqueous solution. So an example of a weak acid would be HCN. And organic acids with the functional group COOH, such as acetic acid, is a weak acid. Now, an Arrhenius base is a substance that increases the concentration of hydroxide ions, OH minus, in aqueous solution. So an Arrhenius base, our key here is our OH minus. And most bases are ionic compounds containing metal cations in the hydroxide anion, OH minus. And they dissociate in water, as shown with the dissociation of sodium hydroxide. So, ammonia NH3 is molecular, and ammonia produces hydroxide ions when it reacts with water. We see in this equation. And the strength of a base depends on the extent to which a base dissociates or breaks apart. Strong bases are strong electrolytes, just like how strong acids are strong electrolytes. And we see our strong acids here: calcium, strontium, barium, sodium, potassium, rubidium, and cesium hydroxide. And we have some weak bases here. Main one we'll talk about is ammonia. So now, monoprotic and polyprotic acids. So a monoprotic acid, before even worrying about what that means in terms of acids, we know mono means one. So a monoprotic acid is an acid that can donate only one hydrogen ion per molecule. So some examples: HClO4, HCl, HNO3, HNO2, right? There's only one ionization step. And here we see HCl, a monoprotic acid, and now we have sulfuric acid, which is a diprotic acid. So we know di means two, so we could have two ionizable steps. And we see here in this picture that we can create two equations or two ionizable steps. So, like I said, polyprotic acid is an acid that can donate more than 1 proton per molecule. There's 2 examples here. A multiple ionization steps, as shown here. Sulfuric acid contains H3O+, HSO4, and SO4 minus 2 ions. So a diprotic acid is the type of polyprotic acid that can donate 2 protons per molecule. So the number of protons, which is hydrogen, okay? So if we have 2 hydrogens, it's a diprotic acid, we're going to have a 2-step ionization process. Triprotic, if we have 3 protons per molecule, that means we're going to have 3 steps. So I'm going to do 2 examples here to show you what I mean. So we already used that HSO4, so we're going to use we'll use H2CO3. And I'll do that right here. So this is the dissociation or ionization of a diprotic acid. So, and I'll use H2CO3. Right? I'm always going to have water here. And one of my products will always be the hydronium cation, H3O, plus 1, plus, so this hydrogen from the carbonic acid is leaving to go to the water. So that's how H3O plus is formed. And our last product is whatever's left from this initial acid. So it'll be HCO3 minus 1. Because carbonate's minus 2, hydrogen's plus 1, so minus 2 plus 1 is minus 1. So now we see we have another hydrogen here, so that means we need one more step. HCl3 minus 1 plus H2O. So this hydrogen is going to leave, go to the water again, and we'll have H3O plus 1 plus CO3 minus 2. Now, when you're looking at your product here, your last product, if you don't have any hydrogens in front of your anion, you're done. The process is over. The first step, we had to do another step because we still had a hydrogen here. We had to get rid of that. And we'll put a forward and reverse arrow because these can go back and forth here. So that's the dissociation of or ionization of a diprotic acid. Now triprotic, all right, so we have H3PO4. Change the color. So triprotic, that means we're going to have 3 steps. So this phosphoric acid is going to lose a hydrogen. It's going to go to water. And this is going to create H3O plus H2PO4 minus 1. Because phosphate is minus 3, we have 2 hydrogens, so 2 times 1 is 2. So negative 3 plus 2 is a negative 1. Now, the first step of this ionization process is just going to be a forward arrow. Okay. Now, when we have our acid as an ion, for the remaining steps, we're going to have a forward and reverse arrow because it can go back and forth. That's why there was a forward and reverse arrow in the second step of a diprotic acid. So we have H2PO4 minus 1 plus H2O. This hydrogen's going to leave and go to the water. H3O plus HPO4 minus 2. And since we have a hydrogen left, we need to use one more step. Once again, this hydrogen is going to leave and go to the water. So we'll have H3O plus H. Oh, no H here. We're done. Should be done. And we're going to have PO4 minus 3. So the number of hydrogens equals the number of steps we're going to have in our ionization of that acid. Okay, so the second acid-base theory or acid-base definition is the Bronsted-Lowry acid and base. So the Bronsted-Lowry acid is a molecule or ion that is a proton donor. So hydrogen chloride or hydrochloric acid acts as a Bronsted-Lowry acid when it reacts with ammonia. Because this hydrogen is going to donate hydrochloric acid will donate its hydrogen to NH3, so HCl would be our Bronsted-Lowry acid in this case. And water can act as a Bronsted-Lowry acid as well, as we see here when it's in a reaction with ammonia. So a Bronsted-Lowry base is a molecule or ion that is a proton acceptor. And don't get confused when you hear the word proton. H plus is a proton, so a hydrogen ion is a proton. So ammonia accepts a proton from the hydrochloric acid. It acts as a Bronsted-Lowry base in the equation below. The hydroxide ion produced in solution by Arrhenius hydroxide bases is the Bronsted-Lowry base. The OH minus ion can accept a proton. So we see here in a Bronsted-Lowry acid-base reaction, protons are transferred from one reactant, the acid, to another, the base. So as you see here, HCl, hydrochloric acid, is our acid, and ammonia is our base. So the species that remains after a Bronsted-Lowry acid has given up a proton is the conjugate base of the acid, that acid. So since hydrofluoric acid is our acid in this case, and it's going to donate its proton to water, that is considered the conjugate base. So Bronsted-Lowry acid-base reactions involve two acid-base pairs known as conjugate acid-base pairs. So our pairs here, we have HF will pair with F minus, and H2O will pair with H3O plus. So strengths of conjugate acids and bases. So the stronger an acid is, the weaker its conjugate base, and the stronger a base is, the weaker its conjugate acid. So proton transfer reactions favor the production of weaker acid and the weaker base. So since we have a weaker acid and weaker base on the product side, the reaction will be favorable to the right. So it's going to go to the right. The reaction to the right is more favorable. In this next equation, our reactants are weaker acids and bases, so that means the reaction to the left is more favorable. And here's relative strengths of acids and bases, a whole chart on these. And it says with increasing strength, so as we go up, we're going to get stronger, and as we go down, we're going to get weaker. So, amphoteric compounds. So, any species that can act as either an acid or base is described as amphoteric. An example is water. Water can act as an acid or a base. And you have two examples here, one where it acts as a base and one where it acts as an acid. Here's a list of some conjugate acid-base pairs. Obviously, you don't have to memorize these. But once you do acid-base type problems, conjugate acid, conjugate base problems, this will sink in. Okay, so amphoteric compounds, the hydroxide in a molecule. The covalently bonded OH, IOH group in an acid is referred to as a hydroxyl group. The molecular compounds containing OH groups can be acidic or amphoteric. The behavior of a compound is affected by the number of oxygen atoms bonded to the atom connected to the OH group. And right here, there shouldn't be IOH. It should just be, so we'll cross this off. It should just be the OH group. Okay, so now we have an example of a conjugate acid-base problem. So we look here. So first thing you need to do with these type of problems, you need to label your acid and your base on your reactant side. So we look here, I have ammonia and I have water. So I know ammonia is a base, and I know water in this case is my acid, right? So water is going to donate one of its hydrogens to ammonia. So since water is an acid, on the product side, hydroxide, the anion, will be your conjugate base. Now, this base here, NH3, accepted a proton. So on the product side, it will be a conjugate acid. Now, last theory or definition, Lewis acids and bases. So a Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. And a Lewis base is a substance that can donate a pair of electrons to form a covalent bond. The Lewis definitions include all Bronsted-Lowry acids and bases. So here we consider the reaction of H plus and OH minus. The hydrogen ion donates itself to the hydroxide ion. H plus is a Bronsted-Lowry acid and OH minus is a Bronsted-Lowry base. The hydroxide ion can bond to the hydrogen ion because it has unshared pair of electrons. OH minus is also a Lewis base, and H plus, which accepts the pair of electrons, is a Lewis acid. So we have a question here. It says identify the Lewis acid and Lewis base in this reaction between ammonia and boron trifluoride. To see which ones can donate lone pairs, or actually has lone pairs, which are electrons, I would draw out your Lewis structure for these. So NH3, plus boron trifluoride, now boron's not going to have any lone pairs because boron's an exception to the octet rule, it can only have 6 electrons. And our finished product should look like this. So now we need to determine which one is our Lewis acid and Lewis base. Let's not forget our definitions for these. So a Lewis acid accepts a pair of electrons. A Lewis base donates a pair of electrons. So ammonia here is donating a pair of electrons to BF3. So since they're donating those pair of electrons, ammonia will act as a Lewis base in this case. And BF3, boron trifluoride, is accepting a pair of electrons, so that means this species is a Lewis acid. And this last slide just talks about the three definitions or theories mentioned in the video. So the Lewis definition is the broadest, and it extends to the two compounds that Bronsted-Lowry theory does not classify as acids and bases. And this concludes our video on acid-base theories and definitions.